All right, the second half of chapter 16. I apologize for the delay. As I was exporting the file from PowerPoint to a video, apparently it got corrupted and completely wiped out my entire narration. So I am re-recording from scratch. Let's get started with the second half of chapter 16. We're going to start with the adrenal glands. And if you guys remember, these are the roughly pyramid-shaped glands that sit on top of the kidneys. And they work to secrete two types of hormones. They're going to be neurohormones and catecholamines. So let's look at the actual structure of these adrenal glands. When you look on the inside, just a regular cross section of these adrenal glands, you're going to find that they have two distinct regions. There's an adrenal medulla and an adrenal cortex. The adrenal cortex is going to be on the outside, and it functions relatively similarly to the other endocrine organs that we've discussed, secreting hormones based on glandular tissue, while the inner medulla is a neuroendocrine organ that works to secrete neurohormones. So the adrenal cortex is divided into three very distinct zones in the middle of a capsule and the medulla. The capsule is going to sit on the outside. The medulla is the medulla layer. The zones are the outer zona glomerulosa, the middle zona fasciculata, and then the inner zona reticularis. And the glomerulosa is going to consist of densely packed cells, while the middle zona fasciculata consists of cells stacked on top of one another. And the cells of the very thin zona reticularis are more loosely arranged in clusters. And each of these do work to secrete very specific hormones. The zona glomerulosa is going to secrete mineralocorticoids. The zona fasciculata is going to release glucocorticoids and androgenic steroids. And then the reticularis is going to also release glucocorticoids and androgenic steroids. And here you see that general structure of the cortex, as well as the inner medulla beneath it. Let's see, I'm going to pick red as my color here. You see that on the outside here you have this capsule of thin epithelial tissue just covering that zona glomerulosa, and then beneath the zona glomerulosa you're going to find that densely packed fasciculata, and then underneath that you're going to find the zona reticularis, relatively thin compared to the zona fasciculata. And then underneath that, you're going to find the adrenal medulla, which again functions to secrete neurohormones, much different to the function of the cortex itself. So, which layer of the adrenal cortex is going to secrete androgens? Which one secretes androgens? It is the zona reticularis, focusing on sex hormones. So the production of the steroid hormones by the adrenal cortex is partially regulated by a multi-tiered feedback system known as the hypothalamic pituitary adrenocortical axis, otherwise known as the HPA axis. And we're going to look at how hormones of the different zones of the adrenal cortex and then how their production and secretion is regulated by the HPA axis, as well as several other factors. So mineralocorticoids are going to be regulating the concentration of certain minerals in the body, like sodium or potassium ions. And the main mineralocorticoid is aldosterone. And so let's look at the actual functions of aldosterone and then how it's regulated. So aldosterone does have several functions. The first of which is going to be maintaining the concentration of extracellular sodium as well as potassium ions and keeping them within their normal ranges. If you guys remember, excitable cells have a sort of high extracellular, low intracellular concentration of sodium, and then low extracellular, high intracellular concentration of potassium. That just means that sodium is in normal cells, the sodium is going to be high in the ECF, low inside the cell. Potassium is going to be the inverse, low outside the cell, high inside the cell. And these gradients are maintained largely by those sodium-potassium ion pumps that we talked about. And the concentrations of these ions in the ECF are also partially maintained by this aldosterone hormone, which works to act on kidney tubules. It stimulates the transcription of more sodium-potassium ion pumps, sodium ion channels, as well as sodium chloride potassium ion co-transporters. And so making all of this has two effects. Sodium and chloride ions are transported from the fluid in the kidney tubules to the extracellular fluid in order to return to the blood. And it also transports potassium ions from the extracellular fluid into the kidney tubules where they will be excreted in the urine. That's just the first function. The second function is it regulates extracellular fluid volume. And aldosterone's effects on sodium and chloride ions in the tubule cells will create a more concentrated interstitial fluid. And so this is going to cause more water to move by osmosis from the fluid in those tubules to the interstitial fluid and the blood. And now this is an indirect effect. Aldosterone has no direct action on the water molecules. It's simply acting on the ions, and because it's putting more ions in the interstitial fluid, water is transporting via osmosis as sort of a side effect. Because blood volume is one of the most key factors in determining blood pressure, aldosterone indirectly maintains the extracellular fluid and blood volume, which in turn maintains blood pressure. Aldosterone's effect on blood pressure is actually a huge part of a larger system involving the kidneys, lungs, and liver called the renin-angiotensin-aldosterone system, RAAS. And this overall physiological functions of this system are to increase blood pressure, preserve blood flow to the heart, brain, and kidneys. We'll talk further about that when we get into 16.2, when we talk about the kidneys as quote-unquote other endocrine organs. And then when we get to talk about the urinary system in chapter 24, we'll talk about it even more. Now, the aldosterone is also going to work to maintain acid-base homeostasis. And because blood is slightly basic at a pH of 7.35 to 7.45, aldosterone helps to maintain this by activating hydrogen ion pumps in certain kidney tubule cells. These pumps are going to transport hydrogen ions from the ECF into the fluid of the tubules, after which they are excreted in the urine, thereby lowering the hydrogen ion concentration in the blood, preserving its slightly alkaline pH. And this figure here shows the general effects of aldosterone, moving sodium out of the fluid in the kidney tubule, moving chlorine out, which thereby moves water out of the fluid in the kidney tubule into the blood. It transports potassium from the blood into the kidney tubules. It's also going to pump hydrogen ions from the blood into the kidney tubules, and in that case, both potassium and hydrogen are excreted in the urine, maintaining electrolyte and acid-base balance. So multiple factors are going to regulate this aldosterone synthesis and secretion. Several of the major ones are, let's say, an elevated blood potassium ion concentration, lowering in the blood pH, and a hormone called angiotensin II, which we'll talk about when we get to cardiovascular system. Now, in addition to this, the HPA axis, inside the HPA axis, there are cortico-releasing hormones, CRH, released from the hypothalamus that trigger the release of ACTH from the anterior pituitary. And the ACTH is going to stimulate aldosterone production and release. Now, hyperaldosteronism, the extra secretion of aldosterone, can lead to a condition called hyperkalemia, which is an abnormally low ECF concentration of potassium ions. It can also lead to hypernatremia, which is an abnormally high ECF concentration of sodium ions, and then high blood pressure. And it can also disrupt that acid-base balance by making the pH of the blood overly alkaline. And this can disrupt many cellular processes. Hyperaldosteronism is generally idiopathic, which just means it's of a general unknown cause, but occasionally it can be due to an aldosterone-secreting tumor. We will talk about the opposite, hyposecretion of aldosterone, later in this module. Now, glucocorticoids are going to be produced in the zona fasciculata and the zona reticularis, and their main function is to help mediate the body's response to stress. Now, as implied by their name, they help respond to this stress by regulating blood glucose. And the most potent glucocorticoid in the human body is the hormone cortisol, also known as hydrocortisone. And its effects are it's gonna target first the tissues of the liver, the muscle, and the adipose tissue, where it's gonna stimulate several different effects. In the liver, cortisol is going to bind to genes of the liver cells known as hepatocytes, and it's going to stimulate them to synthesize enzymes that convert amino acids and fats into glucose via gluconeogenesis. This process is going to raise blood glucose levels. Now, you've also got, in the muscles, you've got the release of amino acids from the muscle tissue. So cortisol is going to break down skeletal muscle into its basic, core amino acids. These amino acids enter the bloodstream, where they're then available for use by the liver in that process of gluconeogenesis. Fat cells, adipose tissue, are going to release fatty acids from the adipocytes to be used by the cells as an alternative fuel to glucose, as well as by the liver in gluconeogenesis. And so for this reason, cortisol acts on adipocytes and triggers a process known as lipolysis, or fat breakdown. And this is going to release those fatty acids into the bloodstream. In addition to this, cortisol has a major role outside of glucose concentration. Most tissues in the body actually have receptors for cortisol, and so it has very wide-ranging effects. One of the most pronounced effects is on the immune system, where cortisol acts as a potent anti-inflammatory agent, reducing the levels of certain leukocytes. And now the strength of cortisol as an anti-inflammatory agent has led to the development of a synthetic cortisol derivative called corticosteroids. And these are what you're going to receive to treat inflammation in a number of conditions. Cortisol is also used to suppress the immune response for, let's say, patients that have autoimmune disorders where their own immune system is attacking normal body cells. They're going to receive cortisol, and then organ transplant recipients also receive cortisol to help prevent rejection of the new organ. And cortical synthesis is primarily going to be controlled by the HPA axis, and CRH from the hypothalamus, which is essentially the first tier of control, is going to be secreted daily in a rhythmic fashion, peaking in the morning hours. CRH secretion is also going to be influenced by parts of the cerebral cortex that may mediate the body's response to sympathetic nervous system and various stressors. CRH stimulates the release of ACTH from the anterior pituitary gland, which acts as the second tier of control. ACTH is then going to stimulate cortisol production, releasing it from the cells of the zona fasciculata, and then this elevated cortisol level suppresses the secretion of CRH and ACTH, thus closing that negative feedback loop. And here you see those tiers of control, the hypothalamus secreting CRH in response to some stimuli detected by the hypothalamus, And then the CRH goes to the anterior pituitary, stimulating the secretion of ACTH, which travels to the the adrenal glands, and stimulates the release of cortisol. And as cortisol levels rise in the blood, the hypothalamus is going to detect that and stop stimulating CRH, which in turn stops stimulating ACTH, which in turn stops stimulating cortisol secretion. Now, because the wide-ranging effects of cortisol are in fact so wide, it probably comes as no surprise that an excess of cortisol in the blood can really disrupt homeostasis. And there are two main causes. There's oversecretion from the adrenal cortex, typically from a tumor. This is called Cushing's disease. And then there's long-term administration of corticosteroids, which may produce iatrogenic Cushing's syndrome. This just means caused by the doctor. And this actually accounts for about 90% of all Cushing's cases. Now, regardless of the cause, the symptoms of Cushing's disease or Cushing's syndrome are the same. It has multiple effects on metabolism. For unknown reasons, that lipolysis induced will become slimmer. The lipolysis induced by the cortisol causes the upper and lower limbs to become slimmer. These fatty acids released by this lipolysis are going to be deposited in the adipose tissue around the trunk, which then becomes heavier. Fat deposits will develop in the face, resulting in characteristically round moon faces. And on the back of the neck, it's going to produce, quote unquote, a buffalo hump. This cortisol also causes muscle wasting due to that chronic release of those amino acids. And the released fats and amino acids are going to be used to make an abnormally high amount of glucose, which is going to consistently raise blood glucose levels, known as hyperglycemia. Now, this and other metabolic effects of cortisol tend to increase appetite, which is going to lead to weight gain. Now, here you see a patient who has developed Cushing's syndrome due to that overprescription or over-administration of corticosteroids. Her face has become rounder, and she's begun really building up those fat deposits. Excess cortisol has effects on other body systems as well. It has a slight mineralocorticoid effect on the kidneys, which can result in greater water retention. Over time, this excess water will increase the volume of blood, raising blood pressure. And then cortisol can also cause the leukocytes to overall sort of suppress the immune system. As a result, patients with Cushing's syndrome have a higher risk of developing both bacterial and viral infections. And then finally, excess cortisol will decrease osteoblast activity and thus interfere with the absorption of dietary calcium, which can lead to bone loss and eventually osteoporosis. Cushing's syndrome is generally treated by removing that ACTH or cortisol secreting tumor. And the treatment for iatrogenic Cushing's syndrome is going to be a little bit more complex since this is a chronic overprescription of that steroid. Many of these symptoms are going to lessen or reverse if the corticosteroid therapy is stopped, but sometimes that isn't an option. Patients with severe joint diseases may not be able to walk without the anti-inflammatory effects. And in such cases, the patient and the physician need to ultimately decide what is best for that patient's quality of life. If corticotherapy is decreased, it has to be done gradually. And we're going to talk about that when we talk about the HPA axis suppression and corticosteroid therapy right now, I think. Nope, we're just totally skipping it. Maybe we'll come back to it later. Now, adrenal insufficiency, this is going to be that hyposecretion of both cortisol and aldosterone, and this is also known as Addison disease. This disease has many causes, including abnormal development of the adrenal gland, deficiency in certain enzymes required to produce these steroid hormones, as well as the destruction of the adrenal glands via the patient's immune system. Addison disease is going to put the patient at risk for an adrenal crisis and can ultimately result in fluid, electrolyte, and acid-base homeostasis disruption. Now, the adrenal production of androgenic hormones, these are essentially going to be sex hormones that affect the reproductive organs, also known as the gonads, as well as multiple other tissues. The majority of androgenic steroids are going to be produced by those gonads, but they are also synthesized in small amounts in both males and females by the adrenal cortex, largely as byproducts of the pathway that yields cortisol. Now, androgenic steroids made by the adrenal cortex have the same general effects of those made by the gonads, but they can actually be converted in the circulation to the androgen testosterone or the female hormone estrogen. We'll talk about the target tissues and effects of these androgens in just a couple chapters. Should be 16.6. Now, if you'll remember, I said the adrenal cortex is going to be endocrine glandular tissue, and the adrenal medulla is going to be neuroendocrine tissue. And the neuroendocrine cells of the adrenal medulla are going to be called the chromaffin cells. And these are going to be derived from nervous tissue rather than glandular tissue. And these are stimulated by that acetylcholine, which is released by preganglionic neurons of the sympathetic nervous system. If you guys remember, a sympathetic preganglionic neuron exits the spinal cord, triggers a postganglionic neuron, which then releases neurotransmitters onto a target cell. Chromaffin cells are very similar to these postganglionic neurons, except they secrete their products directly into the bloodstream, which is why these products are considered neurohormones. Now, as with the sympathetic postganglionic neurons, chromaffin cells are going to release catecholamines, mostly epinephrine and norepinephrine. And chromaffin cells produce and secrete primarily epinephrine. And the reverse is, remember, true for the sympathetic neurons, which primarily secrete norepinephrine. Now, hormonal epinephrine and norepinephrine have almost the same effects on the target cells as the neurotransmitters of this SNS. Specifically, they're going to mediate the body's response to a stressor by increasing the rate and force of heart contraction, dilating the bronchioles, constricting the blood vessels to skin, digestive organs, and urinary organs, while dilating the blood vessels to the skeletal muscles. It's also going to dilate the pupils and decrease digestive and urinary functions. If you remember, we've already talked about additional epinephrine and norepinephrine being secreted by the adrenal medulla, which works to prolong the sympathetic response. Additionally, the epinephrine and norepinephrine from the adrenal medulla have far-reaching consequences. They have a much longer reach. They are able to reach cells that are not innervated by the sympathetic nervous system. That way, the sympathetic nervous system can affect the entire body without requiring a specific innervation for every single cell. And secretions from this adrenal medulla are going to be regulated not only by the SNS, but also by the hormones of the HPA axis. When ACTH is secreted, it can actually directly stimulate epinephrine synthesis via chromaffin cells, and cortisol can increase the synthesis of enzymes required to produce epinephrine. This overall result is a coordinated, integrated response between both the endocrine and the nervous systems, which work together, giving us our best chance of survival when faced with a stressor. We're going to look at a table here in just a second that shows the hormones of the adrenal cortex and the adrenal medulla, and it's just going to sort of summarize everything all together. So you see, I've already talked about all of these and their effects. I'll give you a second just to pause and review. These are all important. You will need to know the hormone, its stimulus, and if you know its stimulus, you pretty much know what will inhibit its release. You need to know its target tissue and its effect. So I'll give you a second just to pause this. All right. Now, as I mentioned, the HPA axis suppression and corticosteroid therapy, we're going to come back to that now. This is that sort of AMP in the real world stuff. All right, so when a patient is discontinuing their corticosteroid therapy, those steroids have to be tapered off very gradually over a period of weeks or months. And this is because that HPA axis feedback is regulating cortisol production and secretion. And when this patient receives high doses of these corticosteroids for an extended period of time, the negative feedback loops essentially halt the production of CRH and ACTH, known as that HPA axis suppression. This means that a patient's body is unable to produce an adequate amount of cortisol for several weeks or even months after the discontinuation of their therapy. Now, the most serious consequence of this suppression is called an adrenal crisis. And this is because cortisol is absolutely vital to survival when a patient is subjected to surgery, trauma, or illness. If they're unable to produce an adequate amount of cortisol in the face of such a stressor, symptoms like low blood glucose, low blood pressure, fainting, vomiting, or convulsions are all possible to develop. If a patient does not get treated for this adrenal crisis, it can easily be fatal. But it can be easily prevented by slowly reducing that dose of corticosteroid that a patient receives, enabling their HPA axis adequate time to resume normal levels of CRH, ACTH, and eventually cortisol production. All right, test yourself. What does thyroid stimulating hormone target? Thyroid stimulating hormone, targets which of these endocrine organs? If you didn't say the thyroid gland, I'm going to be kind of upset. It stimulates the thyroid. Now, which hormone is made by the parafollicular cells of the thyroid? This one's a little harder. Parafollicular cells. Well, you know the follicular cells secrete one kind of hormone, and then you have the parafollicular cells secreting calcitonin. So T3 and T4 are going to be produced by the follicular cells. Calcitonin is produced by the parafollicular cells outside of that colloid follicle. And then parathyroid hormone is going to be secreted by the parathyroid gland. Now, which element is necessary for the production of T3 and T4? Very critical element. If you're missing it, you might develop a goiter. Also, one of the most common radiation kinds of cancers. That's because a nuclear bomb produces fissioning iodine, which easily passes into the thyroid and is easily uptaken by the body. So yes, iodine is completely necessary for T3, T4 production. Now, what stimulates the release of parathyroid hormone? Which one of these releases parathyroid hormone? It is hypocalcemia, low calcium levels. Now, let's talk about the pancreas. Now, the book calls it a club-shaped organ located in the abdominal cavity, mostly posterior to the stomach. I always call it the folded ear of corn. just because it looks like a sad ear of corn that's folded over. The pancreas consists of three major parts. It's got a rounded head, a middle body, and a very thin tail. And it is unusual in both that it is both an endocrine and an exocrine gland. And it is important to note that there are two groups of cells within the pancreas. There are small, round, quote-unquote, islands of endocrine cells called pancreatic islets, and there are exocrine cells called acinar glands. And these clusters of acinar cells are going to be located around small ducts into which they secrete enzymes and other products that are delivered to the digestive tract. Now, the pancreatic islets contain three main cell types through which they work to secrete very specific hormones. You have the alpha cells, which secrete the peptide hormone glucagon. You have beta cells, which secrete the protein hormone insulin. And then you have delta cells, which secrete the peptide hormone somatostatin. Now, remember, I've already talked about somatostatin, and this somatostatin that's produced by the pancreas is identical to the one produced by the hypothalamus. For our purposes here, we're going to focus mostly on the alpha and the beta cells, insulin and glucagon production. And here you see that sad ear of corn with the head, this folded head of the pancreas. Then you have the middle body and a very thin tail. For the histology, it's going to be functionally difficult to differentiate between alpha and beta cells. You see they just are different colors in the illustration, but in the actual histology, it's very difficult to tell what an alpha versus a beta cell is. So as long as you know this that I've circled is a pancreatic islet, also known as an island of Langerhans, if you know that, that's perfect. And then you know all of the surrounding cells out here, these cuboidal tissues, are the acinar cells. Now, which type of islet cells produce glucagon? Remember, we're only focusing on two of them. One of them only produces somatostatin. It's alpha cells. Alpha cells produce glucagon, beta cells produce insulin, and delta cells produce somatostatin, but you may as well forget that. That may be a bonus question if you guys behave yourselves. Now, when we look at hormones of the endocrine pancreas, the biggest job here is regulating the concentration of glucose in the blood. And glucagon's major targets of the cells are the liver, the muscle cells, and the adipose tissue. In these tissues, glucagon is going to promote reactions that increase glucose levels in the blood by breaking down glycogen into glucose. This is called glycogenolysis. There's also the formation of new glucose via gluconeogenesis. There's protein breakdown in muscle tissue to release those amino acids. You've got the release of fats from adipose tissue. And in the liver, you're also going to find that there are new fuel substances created called ketone bodies made out of fatty acids. And ketone bodies are actually formed when the products of fatty acid metabolism are combined to yield a 4-carbon ketone compound. This compound cannot actually be catabolized by the liver in any appreciable amount, and so they're released directly into the bloodstream, delivered to other cells. Some other tissues, like the heart and skeletal muscle, can then take them up and oxidize them. Other tissues, like the brain, are not able to readily oxidize ketone bodies, although under starvation conditions, the brain can adapt and work to generate some ATP from these ketone bodies. And under extreme calorie restriction or starvation conditions, glucagon stimulates that rapid ketone production. However, the cells that use these ketone bodies as fuel are really only able to use so many of them. And so as a result, they can really accumulate in the blood. And if too many ketone bodies accumulate, they work together to lower the pH of the blood, producing a very dangerous condition called ketoacidosis. And uh, glucagon secretion is going to be triggered by several factors, like if blood glucose concentration goes down, if it's being stimulated by this SNS, if circulating catecholamines from the adrenal medulla stimulate it. Interestingly, glucagon is also secreted in response to ingested proteins. And this secretion is part of an integrated hormonal response, ensuring that the blood glucose level remains stable during feeding. Glucagon secretion is inhibited by both elevated blood glucose levels and somatostatin. Now, the primary antagonist of glucagon, glucagon raises blood sugar, insulin lowers blood sugar. This insulin promotes a storage of these nutrients by its target cells if these nutrients aren't immediately needed for fuel. Insulin's primary target tissues are the liver, cardiac muscle, skeletal muscle, as well as certain parts of the brain. In these cells, insulin is going to stimulate an uptake of lipids, amino acids, and glucose. It's going to stimulate synthesis of glycogen in the liver, synthesis of fat from lipids and carbohydrates, and the promotion of satiety, the feeling of being full. And through these effects, insulin replenishes the fuel sources that were depleted during a fasting period and helps to maintain that blood glucose concentration within a very tight range. Insulin is absolutely required for its target cells to uptake glucose. However, in the liver, this is an exception. In the absence of insulin, these cells can be bathed in glucose, yet they'll essentially starve because they cannot take it up. Insulin secretion is going to decrease during fasting and increase during it's going to decrease during fasting and increase during feeding. And the secretion from the beta cells is stimulated directly by a rising blood glucose concentration, and it is inhibited by somatostatin and the SNS. Now, when insulin levels rise too high, free blood glucose level, the blood sugar level, is going to drop. This is called hypoglycemia, and these symptoms include weakness, dizziness, rapid breathing, nausea, and sweating. Severe hypoglycemia can actually lead to confusion, hallucinations, seizures, coma, and even death. These symptoms are generally going to arise because the brain has inadequate glucose to fuel its metabolic processes. Hypoglycemia is most often caused by the over-administration of insulin or other agents that lower blood glucose level. It may also result from prolonged starvation, insulin-secreting tumors, alcohols, poisons, infections, and or genetic conditions. Now, conversely, insufficient insulin secretion or decreased insulin sensitivity can cause blood glucose levels to become over-elevated. This is called hyperglycemia. Two major conditions of which are diabetes mellitus types 1 and 2. Type 1 diabetes mellitus, or insulin-dependent diabetes, affects between 5 and 10% of people with diabetes in the U.S. It's caused by the destruction of those beta cells of the pancreas by the immune system. And this lack of insulin-producing cells means that no matter how much glucose is in the blood, it cannot enter most of its target cells. And so this starves those cells for glucose, and these diabetes type 1 patients feel continuously hungry. There's no satiety. This disease is characterized due to two factors. target cells unable to take in any circulating glucose, and glucose is overproduced in the liver because of unopposed reactions of glucagon. Now, because those alpha cells are the only ones that are broken, beta cells still work perfectly well to produce glucagon. I'm sorry, that's backwards. The beta cells are the ones that are broken, not producing insulin. The alpha cells are still working fine, producing glucagon. Please forgive me for that. This glucagon is also going to elevate the number of ketone bodies in the blood, and this increased concentration of glucose and ketones can lead to the presence of more glucose and ketone in the fluid in the kidneys, thus leading to a condition called glucoseuria and ketonuria, meaning that there's glucose in the urine and ketones in the urine. The glucose and ketone bodies in the kidney fluid makes that more concentrated than normal, and so less water than usual is going to leave the kidney tubules by osmosis, causing water retention, and this is a condition known as osmotic diuresis. Now, this activity also causes two other common symptoms of diabetes type 1, frequent urination, known as polyuria, and dehydration caused by excessive thirst, polydipsia. Now, the only treatment at current time is insulin administration via injection. Type 1 diabetes requires strict monitoring of diet and blood glucose levels to ensure that the level doesn't rise too high or fall too low. If a patient fails to closely monitor their disease, they can really quickly accumulate a huge number of ketones and decrease their pH of their blood. This is called diabetic ketoacidosis. This condition can actually lead to coma and even death from nervous system shutdown. I apologize. I just realized I was not moving through the slides as I was talking. So polyuria, polydipsia, and now we're into type 2 diabetes. Type 2 diabetes mellitus, also known as non-insulin dependent diabetes mellitus, is the much more common form of diabetes. Up to 95% of people that are diabetic patients suffer from type 2 diabetes. This form generally develops in adults, and so it was formerly referred to as adult onset diabetes mellitus. But patients with type 2 diabetes generally still have functional beta cells capable of producing insulin, but their beta cells do not respond to the normal increases in blood glucose, and other target cells are actually less responsive to their insulin. This is an effect called insulin resistance. This results in hyperglycemia and that accompanying characteristic sign and symptoms like glucoseuria, polyuria, and polydipsia. However, type 2 diabetics generally produce enough insulin to keep ketoacidosis from developing. The development of type 2 diabetes is strongly associated with heredity, genetic conditions, as well as obesity. Now, poorly controlled type 2 diabetics are really the same symptoms as poorly controlled type 1 diabetics. Damage to the blood vessels, peripheral nerves, the retina and the lens, and the kidneys. Patients with type 2 diabetes seem to be at a higher risk for these complications, probably because the signs and symptoms of hyperglycemia in these individuals are often vague, which can lead to a delay in diagnosis and treatment. By contrast, signs and symptoms of type 1 diabetics are much more immediately evident because these individuals produce no insulin, and so diagnosis and treatment are much earlier. Now, nearly all type 2 diabetics are advised to make lifestyle changes to incorporate weight loss, healthy diet, and regular exercise. In fact, some patients are able to manage the disease with lifestyle modification alone, but many require additional treatment. And one of the most common treatments is a type of drug called oral hypoglycemics, which lower the circulating blood glucose level. And occasionally, type 2 diabetics will require insulin therapy to maintain a stable blood glucose concentration, but this is really not a mainstay treatment for most patients. Now, as we've already talked about, insulin and glucagon sort of act antagonistically in a negative feedback loop, regulating blood glucose concentration. But this is a little bit more complex than most feedback loops because both insulin and glucagon are going to be secreted during feeding to maintain blood glucose homeostasis. The regulation of blood glucose level is going to be talked about here. So, the first thing is the stimulus, okay? Blood glucose level is going to rise, typically in a result of feeding. It can also rise due to several hormones like cortisol. And then the receptors, these beta cells of the pancreas, are going to detect that increased blood glucose concentration. And just like alpha cells, beta cells act as sensors detecting that increase in blood glucose level. And so these beta cells are now going to act as a control center, regulating the secretion of insulin. And so the same stimulus reduces that glucagon secretion from alpha cells as well. So this rise in blood sugar is going to promote the secretion of insulin and inhibit is the word I was looking for, the secretion of glucagon. Now, there's the effector response. This insulin is going to act to decrease the blood glucose level by increasing glucose uptake by various cells, storing that glucose, those amino acids, and fats. Now, these effects are going to be balanced by a slight increase in glucagon secretion, which responds to those proteins in food. This prevents any hypoglycemia from affecting the individual, especially if that food that they ate contains limited carbohydrates. Now, homeostatic range. As the blood glucose level returns to its normal range, the negative feedback loop to the beta cells is going to decrease the insulin production. So as you just ate, you raised your blood glucose level, but now that this insulin is taking effect, it's falling back down, and so the beta cells are going to notice that, and they're going to stop or slow insulin secretion, which decreases those responses, and in such a way that the blood glucose level never falls very far below normal range. And here is that figure where we see, oh, we are eating, blood glucose has risen, so the beta cells act to secrete, they notice that there's a lot of glucose in the blood, and so they work to secrete insulin, which stores that glucose in cells, and then free blood glucose levels in the blood fall back down into homeostatic range. In the opposite direction, it's pretty much the same, just in reverse. Let's say an individual is fasting, they're going to their blood glucose level is going to dip below its normal range, and so alpha cells of the pancreas are going to detect that low blood glucose, and the control center, these alpha cells, are going to increase their glucagon secretion. This is then going to, at the same time, this glucagon secretion is upregulated, insulin secretion is deregulated, it's downregulated. The effectors, glucagon increases the blood glucose level by triggering the breakdown of glycogen into glucose. So this excess glucagon is going to trigger glycogenolysis, I'm going to get it right, glycogenolysis, as well as gluconeogenesis. Both of these work to raise the blood glucose level. In addition, this is going to increase availability of other fuels like ketone bodies, free amino acids, and fatty acids. And eventually, blood glucose level will realign itself to normal range, and alpha cells are going to notice that the blood glucose has returned to normal. They're going to decrease glucagon secretion, which decreases the response through negative feedback. And again, you see it here. It's just inversed. So blood glucose falls low. Alpha cells notice this, so they upregulate how much glucagon is done. This glucagon goes to the target cells and says, turn that glycogen back into glucose. Give me the glucose. And the free glucose then flows through the blood, raising blood glucose level back to that normal range. And here we see those, this is just the table showing the various quote-unquote other endocrine organs. We see the pancreas, we see the thymus. We'll talk more about the thymus in just a little bit, but it is also important. Now, what hormone lowers blood glucose levels? I've just talked about this a whole bunch, so you guys need to know. Lowers blood glucose levels. It's insulin. Insulin lowers blood glucose. Glucagon releases blood glucose from glycogen back into the blood. You know what I mean. Now, 16.6. This is going to be the other endocrine glands as well as various hormone-secreting tissues. And so the thing you want to remember here is there are only 7 endocrine glands, but there are also various tissues that secrete hormones. So all endocrine glands are tissues that secrete hormones, but not all tissues that secrete hormones are endocrine glands. I hope that makes sense. So the first one we're going to talk about is the pineal gland. The pineal gland is going to, it's a part of the epithalamus, the posterior region of the diencephalon of the brain. And it works to secrete the neurohormone melatonin, which appears to be to regulate light and dark cycles. The pineal gland actually begins secreting this melatonin when ambient light decreases, so this is in the evening, reaching its peak secretion throughout the night. Melatonin's main target tissues are those sleep centers in the reticular formation of the brainstem, where it appears to sort of adjust that sleep phase. Synthetic melatonin is often sold as a dietary supplement. And its effectiveness for these people is questionable. So for some, they swear it works, but the placebo effect may actually be what's happening there. Now the thymus, this is actually an irregularly shaped organ found on the mediastinum. And this is the site where T lymphocytes, which are a class of leukocytes, which are white blood cells, this is where those T lymphocytes mature. And these T lymphocytes are going to be involved in the immune response. The thymus also secretes thymosin and thymopoietin, which function mainly as paracrine signals. So if you remember, there's endocrine, autocrine, and paracrine. These paracrine signal nearby cells. So these paracrine signals assist in T lymphocyte maturation. Now, the thymus gland is generally much larger and far more active in infants and children who are still developing their immune systems. In adults, the thymus will atrophy or shrink and is mostly replaced with adipose and other connective tissues, generally just over the heart. The gonads, we're going to talk about sex hormones. In biological males, those are the testes. In biological females, those are the ovaries. These gonads are going to be responsible for production of gametes, sperm in males, ova in females. But additionally, they produce the sex steroid hormones that are responsible for this gamete production. They also have these sex hormones also have multiple other functions throughout the body. So let's look at these specific hormones. Testosterone is produced by the testes mostly. Although testosterone is considered the quote-unquote male hormone, females do produce small amounts of it. Remember, the adrenal cortex produces a little bit of each of these two cholesterol-based hormones. Testosterone production and secretion in the males are regulated by a multi-tiered negative feedback loop involving the hypothalamus and the anterior pituitary. So gonadotropin releasing hormone from the hypothalamus is going to stimulate the release of both luteinizing hormone and follicle stimulating hormone from the anterior pituitary. Luteinizing hormone stimulates testosterone synthesis, and follicle stimulating hormone stimulates a production of a protein that binds testosterone and concentrates it in the testes. Through a negative feedback loop, however, any high levels of testosterone are going in the blood are going to decrease that gonadotropin releasing hormone secretion and thus decrease luteinizing hormone and follicle stimulating hormone production. Now, just like all steroid hormones, testosterone is hydrophobic, so it easily crosses plasma membranes of basically all cells. Then it binds to an intracellular receptor and influences gene expression. This testosterone has two basic effects. They're either anabolic or androgenic. Anabolic effects are those that stimulate bone growth and muscle mass. Androgenic effects are the quote-unquote male generating hormones. And these encompass those involving the development of males' secondary sex characteristics like facial hair, deeper voice, increased bone and muscle mass. And these are often called the secondary sex characteristics because the affected organ is not part of the reproductive system. Biological females have the ovaries, which produce the female steroid hormone known as estrogen. And in parallel with testosterone, estrogens are considered female hormones but are produced in smaller amounts in males. Again, the adrenal medulla is fully capable of secreting both. As with testosterone, the secretion of estrogens is going to be regulated by gonadotropin releasing hormone from the hypothalamus, which then stimulates luteinizing hormone and follicle stimulating hormone from the anterior pituitary. Male and female brains work the same biologically. Estrogens stimulate the development of females' secondary sex characteristics like the breasts. They regulate the menstrual cycle and have multiple effects on other tissues and organs like the bones, blood, kidney, and adipose tissue. But that's not the only steroid hormone produced by the ovaries. There's also progesterone. Progesterone production peaks directly after ovulation and during pregnancy. Progesterone has multiple physiological effects, many of which work to help prepare the body for pregnancy and then support fetal development during pregnancy. It also affects smooth muscle tissue, body temperature, blood clotting, bone tissue, and metabolism. And we will talk much, much more about the physiological effects of estrogens, progesterone, and testosterone when we get to the reproduction and development chapter, chapter 26. Now, which hormone does the pineal gland secrete? Pineal gland. Where is that pineal gland? What does it do? What does it secrete? It secretes melatonin. This is the day-night cycle regulator in the pineal gland. Now we're into the other tissues that secrete hormones. Now, fat tissue is also fully capable of secreting a protein hormone known as leptin. And although it is a protein, leptin easily crosses the blood-brain barrier to interact with its main target cells, hypothalamic neurons controlling feeding. Leptin acts on these neurons to induce satiety, that feeling of fullness, preventing overfeeding. Now, interestingly, leptin amounts secreted appear to be related to the amount of adipose tissue present. In theory, this should prevent humans with excess adipose tissue from overeating. However, the mechanisms that regulate feeding are really rather complex, involving multiple neural and hormonal factors. We'll talk about this in just a little bit for A&P in the real world. Oh, right now, actually, we'll talk about it. So, because leptin does induce the satiety, and because obese people have more adipose tissue, they should more readily feel full. The hypothesis here was that leptin supplements would suppress the appetite and lead to weight loss. Unfortunately, research has demonstrated that administered leptin was not effective at reducing human appetite. However, this hasn't stopped many manufacturers of over-the-counter dietary supplements from marketing their leptin-containing supplements as a miracle weight loss solution. It's just the science isn't there yet, and because there's neurological components, there's hormonal components, there is no one magic bullet for weight loss. Now, the heart also secretes various hormones. Cardiac muscle cells, which contain the stretch-sensitive ion channels, these channels open much more widely when the blood volume inside the heart increases, and this is going to stimulate the cardiac muscle cells to secrete atrial natriuretic hormone, or ANP. This ANP has two main target tissues: smooth muscle cells lining the blood vessels and the tubules of the kidney. So in blood vessels, this is going to relax the smooth muscles there, creating a vasodilation, increasing vessel diameter. In the kidneys, it enhances excretion of sodium ions, a process called natriuresis. The process of natriuresis also enhances water excretion because it makes fluid in the kidney tubules more concentrated, pulling that water out of the interstitial fluid in the blood. Now, this causes less water to be retained by osmosis and more water to be excreted in the urine, lowering blood volume and lowering blood pressure. And the kidneys are going to serve several roles as far as hormone production goes. They produce erythropoietin, also called EPO. And EPO is secreted mainly by cells in the kidney in response to low levels of oxygen in the blood. EPO acts on red bone marrow, stimulating the development of erythrocytes, red blood cells, which increases the blood's oxygen carrying capacity. We will talk about a little bit about EPO in the red blood cell chapter, the chapter on blood, chapter 19. Now, kidney cells also secrete renin, and this is an enzyme in the blood that converts plasma protein angiotensinogen into angiotensin 1. This is an important part of the renin-angiotensin-aldosterone system, the RAAS, which maintains that blood pressure. The kidney also converts vitamin D from an inactive form into an active form. This is the calcitriol form when it is active. Recall that this change is stimulated by parathyroid hormone. Now, the hormones, target tissues, and effects of the pancreas, endocrine glands, all of those covered in this chapter, are summarized in table 16.4 in your book, but I also have a couple of them here. So these are the gonads, males' testes, females' ovaries. You can pause here, see their hormones, their target effects, target tissues, and their effects. And then here you have the hormones produced by other endocrine organs and hormone-secreting tissues. So these are the non-endocrine gland hormone-secreting tissues: the pineal gland, the adipose tissue, the heart, and the kidneys. I'll give you a second to pause and jot this down. Remember it. Now, thymosin and thymopoietin assist in the maturation of what? This is out of the thymus, and the thymus is absent in adults. So this is in children. They're the T lymphocytes of that still developing immune system. Now we're going to talk a little bit about how the endocrine system responds to various stressors. Now, let's look at these. So, fluid homeostasis is the first example we're going to look at here. And this is the maintenance of a necessary volume of water in the extracellular fluid. Now, several hormones indirectly contribute to fluid homeostasis, but the three main water-regulating hormones are antidiuretic hormone, aldosterone, and atrial natriuretic protein, ANP. So, let's look at their interactions. Under normal conditions, low levels of ADH and aldosterone are secreted continually, and this leads to an average urine output. The hypothalamus and the adrenal cortex continually secrete very small amounts of ADH and aldosterone, and this is necessary because huge volumes of blood are filtered through the kidneys every minute. In fact, the equivalent of the entire volume of blood plasma flows through the tubules of the kidneys about 60 times per day. Therefore, ADH and aldosterone are continually secreted to ensure that most of the plasma volume is not lost to urine. Now, aldosterone's important effects on the electrolyte and acid-base homeostasis provide another reason why it must be continually secreted. When there's a decreased plasma volume and an increased plasma solute concentration, ADH and aldosterone levels rise, leading to a decreased urine output. So this just means there's low amounts of water in the body, and so ADH, antidiuretic hormone, and aldosterone work to retain water, leading to a greater water retention and lower output. If the opposite is happening and the plasma volume increases while solute level decreases, ADH and aldosterone secretions decline and ANP secretion increases. This leads to an increased urinary output. Excuse me. If plasma volumes continue to rise, this ANP secretion from the heart is triggered. Together, these changes in hormone secretion result in a water loss from the blood through an increased urinary output. And so here you see those three conditions. I'm just going to draw a line here, just separating them. But oops, that was a big curve. I've already discussed what happens here. So normal urinary output through normal conditions, low blood plasma volume, high blood solute concentration, less urine, you see lowered urinary output. If there's too much plasma and not enough solutes in it, then we're going to secrete more urine to lower that, to balance that fluid homeostasis. Now, for metabolic homeostasis, it's a little bit different. This is the most complex example because it involves several different factors. You have to control the metabolic rate of different cell populations. You have to ensure fuels are available. You have to store fuels during times of rest. You have to regulate growth. You have to regulate feeding behaviors. We're going to simplify this by looking at hormones that maintain metabolic homeostasis during 3 periods: at rest while fasting, at rest while feeding, and during exercise. Now, at rest while fasting, thyroid hormones determine the basal metabolic rate. So if you remember, T3 and T4 set that metabolic rate, that BMR, basal metabolic rate, by triggering processes that would cause the body cells to consume ATP. This ATP generation maintains body heat, also stimulating gluconeogenesis, leading to an increase in blood glucose concentration. And during fasting, this increase helps maintain a stable blood glucose level. Fasting also triggers the release of glucagon and an elevated level of growth hormone, which further raise that blood glucose level. Now, at rest while feeding, insulin secretion will increase. And as feeding begins, this increase in blood glucose concentration causes insulin release. The insulin triggers that glucose uptake via target cells and the storage of any excess glucose as glycogen and fat in adipocytes. This presence of protein in a meal will lead to growth hormone and IGF-1 release, which are going to stimulate protein synthesis with the ingested amino acids. And then protein in a meal also stimulates glucagon release to prevent low blood sugar in the event of a carbohydrate-poor meal. Feeding ends with both the help of insulin and leptin, promoting satiety in the hypothalamus. During exercise, you're going to find that catecholamines control the metabolic rate and glucagon secretion is going to increase. As exercise begins, the SNS increases catecholamine secretion from the adrenal medulla. Catecholamines in the blood cause metabolic rate of all cells to increase to a level higher than the metabolic basal rate set by the thyroid hormones. This increased metabolic rate necessitates more metabolic fuels, and for this, alpha cells of the pancreas increase glucagon secretion. These actions are further discussed when we look at the stress response, which we're going to talk about here. So here you see just a very in-depth view of it. It may be a little blurry, but essentially this person is exercising, and that exercise is essentially a stressor. And so the initial response is going to be the hypothalamus releasing GHRH and CRH, okay? And these cause the anterior pituitary to release growth hormone and ACTH. The hypothalamus is going to activate then the SNS, the sympathetic nervous system, at the same time. So following the release of growth hormone and ACTH and the activation of the sympathetic nervous system, these same things happen at the same time. ACTH and the sympathetic nervous systems trigger the release of cortisol, aldosterone, and catecholamines. And then at the same time, the sympathetic nervous system triggers the release of glucagon from the pancreas. After that aldosterone is created, it increases sodium and water retention in the kidneys, increasing blood pressure. All of this following down to the liver and the adipose tissue, working to generate glucose and fatty acids together with the growth hormone, the cortisol, the catecholamines, and the glucagon, triggering that increased release of metabolic fuels, both from the liver and from the adipose tissue. All of this to really just regulate the balance the necessary for homeostasis. All right, that is it for chapter 16. After this, you guys have the test for us. That is on Friday. So I look forward to you guys taking it. I apologize for this being late. I have no reason other than technical issues. Hopefully it won't happen again. I just apologize for that.